Okay. So, in the last lecture, we went over electrostatic potential energy. In the introduction of the electrostatic potential energy, we had a look at what the electrostatic potential energy actually is. And we thought of the thing that when a capacitor is charged, where does the energy expanded by the voltage source really go? And then we concluded this topic with the fact that the energy gets end up getting stored in the dielectric medium that is in between the plates of that capacitor. After that, we calculated the value for that we, a generic value, a generic expression, and then we converted it for parallel plate capacitor. In the end, we talked a little bit about electrostatic energy density. uh, that basically is that the same amount of work that was done in moving the charge q while charging a capacitor from its uncharged condition to fully charged condition per unit volume. Now, the topic for today is basically the goal for today is to figure out what the force actually here is. Now we need to know which force we are talking about. The force basically in a for example in a parallel plate capacitor, oppositely charged plates of uh, a conductor, basically they are attracted by an electric force. The force acting on any system of charges may be obtained from energy considerations. That means that whenever there are two plates which are oppositely charged and they are separated by a dielectric and they are placed in front of each other, then there we know that there is a charge on if there is a positive charge on the upper plate and a negative charge on the lower plate, then there will be a force which is basically keeping these charge surfaces bound, these the charges on these surfaces bound. That force basically is the thing in which the electrostatic energy gets ends up getting stored. So now the goal is to find the value of that force which is keeping those charges on the surface of those conductors constant, and which is basically behind the energy that is stored in between these two plates. So, if there are two conductors comprising a capacitor and they are allowed to move closer, now we know that there is some kind of force, but which is connecting the positively charged plate to the negatively charged plate. But the thing is that we don't allow these conductors to move toward each other. These conductive plates basically are fixed. We don't allow them to move. So that is why that force which is connecting or binding this positively charged plate to the negatively charged plates, we say that this force is not being expanded, but it basically is storing that energy. Now what he's saying is that if these two conductors which are comprising of a capacitor, they are allowed to move closer, if we allow them to move under the influence of that force which is in between those plates to each other and under the influence of electric field, the force acted by that electric field, and as a result these two plates they move a little bit closer to each other, and we name that length to which these two plates moved as dl, the differential length. But the thing that we need to know here is that we have to maintain the charges on the plates. We have to keep the charges on the plates constant, because we don't want the value of rho s to change, because if the value of rho s changes, then this corresponds to electrodynamics, but we are dealing in electrostatics, so we need the value of rho s to be constant. We need the value of charge that is present on that place to be constant. So the thing is that he's saying that we will allow these two plates to move towards each other under the influence of that force which is stored in the form of electric field in between the dielectric, and this movement is we have named that length as a dl. But the thing is that we have to maintain the charge on that plate, or we have to keep the charges on that plate constant. So the as a result, when these two plates move to a distance of dl, differential length dl, then the mechanical work done by the charged capacitor is to What will be the value of mechanical work done? We know that the value of work is basically F dot dl. Here dl is basically the amount of distance that these conductors have covered in order under the influence of this force, which is due to the presence of positive and negative charges, or due to the presence of the electric field in between them. So the mechanical work is done by expanding electrostatic energy. Now we know that there is only that energy, and this force was also as a result of that energy which was stored in the form of electrostatic energy. So if we are allowing these two plates to move towards each other, that means that we are in fact allowing that force, that electric field that was in between these two conductors, to do some kind of mechanical work. So the expenditure of energy in order to move these two plates towards each other, that is due to that uh, energy which is stored in between these plates. So the dw is equal to the loss of energy stored in electric insulating material of a capacitor. So the yeah. So dW, basically the amount of mechanical work, is the expenditure of the electrostatic energy. The dWe is basically electrostatic energy which is stored in between those capacitor plates. Electrostatic energy that was stored in between those capacitive plates. So the mechanical work that is being done, it is basically being done on the expenditure of that stored energy. Now we know that there was an expression we studied while studying the gradient, the concept of gradient. That expression was the change in temperature was equals to the gradient of temperature dot the amount of distance that it covers. So if we convert it to work, we know that work is a scalar quantity as well. So that will be the gradient of work. This is the electrostatic potential energy. The gradient of electrostatic potential energy dot the distance that it covered due to the expenditure of this electrostatic potential energy. So what he's doing here is that he's putting the value of minus dWe. So the mechanical work is now equals to minus gradient of electrostatic potential energy dot the distance that it covered, the dl that it covered. Now we have two equations of mechanical work. The first one is this, the second one is this. We will compare 1 and 2, and we will find out the value of f. If we compare these two equations, we know that this f corresponds to this thing. So the force f is basically the gradient of electrostatic potential energy that was stored, and the unit for this will be Newton. So we found the value of, yeah, we calculated the value of a force that was doing all the work if we allowed the capacitors to move towards each other. So this force is basically the force which is doing mechanical work. Now to apply this for a parallel plate capacitor, this is a more generic form of this equation, and if we want to extrapolate, if we want to be specific about a parallel plate capacitor, then all we have to do is that we need to uh, see what was the value of electrostatic potential energy for a parallel plate capacitor. That was 1 over 2 q square over c. And if we put the value of c, which was for parallel plate capacitor, epsilon a over d. Now if we change this notation d to z, because we are talking about parallel plate capacitors, and if we place parallel plate capacitor in xy plane, then this movement, the dl, this will be in the direction of z. So we are changing the value, the notation of this d here to z. So we are rewriting this equation as epsilon e over z. So this is the value of capacitance. If we put this value of capacitance here in this equation, then we will get q square z over 2 epsilon a. Now we have the equation for we. We are doing this because we need to calculate the value of force, and in order to calculate the value of force, we have to calculate the gradient of this we. So for parallel plate capacitor, we have put the value, the actual value of we. Now if we calculate the value of F, that is minus gradient of WE. So the WE is only according to the Z. So all the other unit vector, they will be equals to 0, and the only thing that remains is minus Z hat partial over partial Z into Q square Z over 2 epsilon A. All of these things are constant, and the derivative of Z is obviously 1. So the value of F will come out to be minus Z hat Q square over 2 epsilon A. So this is it. Now we know that for parallel plate capacitor, the value of Q is epsilon A and E. How did we calculate the value of this? We know that we found the value of E for parallel plate capacitor to be Q over epsilon A. If we reflect back to the example that we solved, the example related to parallel plate capacitors, you will remember that we calculated this value of E. So now he is putting the value of Q in terms of electric field. So he's putting epsilon A E to make it more simplified. So epsilon A E square divided by 2. This value of F is for parallel plate capacitors. You can extend this concept to any kind of capacitor. You can extend this concept to the coaxial cable one that we studied in the example 4-12, I guess. For that, you need to put the value of WE with respect to that coaxial cable or that round capacitor. We calculated the value of WE for that thing there. So all you had to do is to put the value of that WE in this equation, and then you need to calculate the gradient. The resultant will be the value of force. This is the force actually which is binding these two plates together. Yeah, this is the force actually which in the form of which the energy is being stored in between the dielectric, which is in between these two conductors. So uh, the next thing that we will study today is the concept of image method. Image method. Now we need to know that what image method is and why do we need this kind of method, and what is the use, what is the application of this thing, and why can't we rely just on the Coulomb's law or the Gauss's law or the voltage potential. We have almost three ways now to calculate the value of electric field, capital E, but why do we need a fourth method to calculate the value of electric field? For that, in order to understand the requirement, the need for this method, we will talk about a special scenario. In that special scenario, what we have is that we have an unlimited length of a conductor, and as you know, this is a conductor and it is connected to ground, so the voltage at this conductor will be equals to 0. Now what we have is that we have a positive charge which is placed right here at the z-axis. Now you have to consider that this conductor is lying in that xy plane. Same thing that we discussed, the example of that table. The table is basically the conductor, and we are holding a charge above it at the z-axis. So we have a charge here. So as it is a, we will assume it to be a perfect conductor, so we will say that its conductivity is maximum. Now he says that we will consider a point charge q at a distance d. The distance, this distance is termed as d. So we will consider a point charge q at a distance d above an infinite perfect conducting plate. We want to calculate the value of V, or we want to calculate the value of E at any point above this plate. We want to calculate the value of E above this plate, or we want to calculate the value of V. Also, we need to calculate the value of rho s that will be induced on the surface of this conducting material due to presence of this charge. We know that whenever we place a charge in the vicinity of any conductor, that charge will induce some kind of charge density on the surface of that conductor, because it has to maintain zero electric field inside it. So we need to calculate the value of rho s on that plate too. Now, what are the two methods or three methods that we had if we want to calculate the value of E for above the conducting surface? So first of all, we had Coulomb's law. Why can't we use Coulomb's law? Because Coulomb's law basically requires magnitude and location of all charges. As you know, that we in Coulomb's law we had 1 over 4 pi epsilon, and then we had q into r1 vector divided by r1 magnitudes cube. So we need to have the value of r1, or we need to have the value of magnitude of that r1. But we can find the value of r1 if our observation point is here, and this will be the value of r1. But what about this thing right here? We don't know where the point charge exactly is, so we can't calculate the value of r for this kind of thing. So in this case, the q induces an unknown non-uniform distribution of charge on the plate, and this makes impossible for us to calculate the value of that r, that magnitude and location of r charges, because we need to have the location of charges if we want to calculate the value of E by using Coulomb's law. So we do not have uh, the value of uh, location, sorry, the location of charges. I need to write the location of charges that are on this plane or above this. So we need to reject the idea of Coulomb's law. Now the next thing that we'll turn to is Gauss's law. And for Gauss's law, the main requirement was that we needed to think of a surface that encloses all the charges that we're talking about in such a way that the value of, or the field lines, the electric field lines should always be perpendicular to the surface of that imaginary surface, should always be perpendicular to the Gaussian surface. Now, this thing is difficult for us to follow here, because we do not know what kind of, uh, as the geometry of this conducting material is infinite, we do not know what kind of a shape this conducting material has. So it is almost impossible for us to imagine a surface, imagine an imaginary surface, a Gaussian surface, such that the electric field lines are always perpendicular to that surface. So if we can't imagine a surface, if we can't think of a Gaussian surface which fulfills this requirement, then the answer that we will calculate by integrating that surface, that is going to be an inaccurate one, and that will defeat the purpose of calculating of us calculating the value of E. So this is not possible for us either. Now moving on to the third thing that we had, E is equals to minus gradient of V. For this thing too, we need to calculate the value of V, and if we want to calculate the value of V by using this non-uniform rho s that is induced on the surface of this conducting material due to the presence of this positive charge, that is going to be a lot more difficult process. So we will say that it has very complicated mathematical computations. So we need to reject this idea too. That means that all the three conventional methods that we had in order to calculate the value of E, they are being failed here. So here comes another method which we call the image method. In an image method, for any given charge configuration above an infinitely perfectly conducting plane is electrically equivalent to the combination of given charge and its image configuration with conducting plane removed. Now what he's saying is that if we have this kind of configuration that is mentioned above like this, and we have a infinitely conducting conducting surface here, and this is basically the value of D. He's saying that this is actually equivalent to the image. What is the image? We know that everything we see in a mirror is reflected, so this is D. If we see this thing in a mirror, we will see this charge at a distance of D once again, but the image will be reflected. So we have removed that conducting plane, but instead of it, we have changed it. We have replaced that infinitely conducting plane with the image of that charge that was placed in through some distance of that conducting plane. So what we did here was that we removed that conducting plane, and we have essentially made an image of that charge below. So now we have a dipole. As we have a dipole, so it is now very easy for us to calculate the value of E at any given point, because now we have an exact location of this charge and we have an exact location of this charge. All we have to do is that we have to put the values of R1 and R2 and so on and so forth into the equation of Coulomb's law, and calculate the value we will calculate the value of E very easily. So by this method we calculated the value of E, but the other goal was to calculate the value of V. So if a charge resides in the presence of more than one grounded plane, yeah, we need to talk about this too, which means that if we will do this when we have only one plane. Now what if we have another plane right here? Now there are two planes. We have this plane and then we have this plane. So we will eliminate this conductor, but in order to eliminate this conductor, we will have to consider an image of this charge here too. So we will see what is the distance of this charge from this plane. Let's suppose it is Z. So there will be an image which will be at Z from the conducting plane. So we will imagine an other image or mirrored image of this charge for this plane too. So it doesn't matter how many planes, how many conducting planes you have. All you have to do is that for in order to eliminate that conductive plane is that you need to imagine an image of that charge, and then you can eliminate that conductive field. तो अगर आपके पास ये दो fields हैं, तो what you need to do is that you need to eliminate these two conductive fields by replacing them with an image of that charge. It doesn't matter how many planes there are. Okay, so image method applies to charge distribution as well. Uh, Once the value of E is found, the charge distribution induced on the plate can be found from. If we have the value of E, just like in this example, we basically conceptualized how to find the value of E for this dipole. And when we have the value of E and we want to calculate the value of rho s, now we have the value of E by using Coulomb's law, and we want to calculate the value of rho s, and we know that For a dielectric conductor boundary, the value of E will be n dot E is equals to rho s over epsilon. And if we know the value of permittivity and we know the value of E, it is very easy for us now to calculate the value of rho s. That will be n dot E into epsilon. So the main thing was to calculate the value of E. Once we have the value of E, we can calculate the value of rho s, which was induced on the surface of this conducting plate. And apart from that, if we know the value of E, we will calculate the value of V very easily by using this expression that we derived earlier, and we have applied this expression to various conditions. So there is an example related to this thing, related to this image method, and that example basically is exactly involves the exactly same scenario that we have discussed in this topic. For that example, he says that we have a positive charge, and the coordinates of this positive charge is 0 0 d, and we have an infinitely conducting plane here at 0 0 0 coordinates. Now he wants us to calculate the value of E at this point, at observation point x, y, z. So he says, how do you calculate the value of electric field at this point? So by image method, we will replace this conducting plane. We know that the coordinates of this charge is 0 0 d. That means this charge is at the distance d. So if we want to imagine an image that will be on the coordinates 0 0 and minus d, and as the image is always reflected, so now it is minus q. So this is one vector. We will say this is r1. This is the second vector. We will say that this is r2, charge to observation point. So the value of E will be 1 over 4 pi epsilon naught q r1 over r1 cube plus minus q r2, sorry, r2 over r2 cube. Now what we'll do here is that we will take the q common, q over 4 pi epsilon, and we will put the values of this r1 in order to calculate the value of this r1. We know what will be the value of r1, x minus 0, that is x hat, x plus y hat, y minus 0, this is y, plus z minus d, so z hat, z minus d, this is the value of r1. If we want to calculate the value of r2, this will be x hat, x plus y hat, y plus z hat, but now z minus minus d, so z plus d. So we will put the values of r1 here. This is x hat, x plus y hat, y plus z minus d, z hat, this is the actual vector, divided by under root x square plus y square plus z minus d square and the cube of this thing, minus x hat, x plus y hat, y plus z plus d divided by x square plus y square plus z plus d square under root and the whole cube. So this is actually the value of E for this thing. So this example is over. This is example 4-13. I hope you understood what the concept of an image method is. This was given to b is equals to 0. And what is the application of this image method? The next thing that we're going to study is magnetostatics. We will be moving towards the next chapter, which was related to magnetic field but under static conditions, and the postulates uh, related to magnetostatics. The postulate related to these magnetostatics are basically the divergence of B will be equals to 0, and the curl of H is equals to J. This J is current density. As we know, we have studied current density too many times up till now. So we knew that the divergence of B is equals to 0. What is the physical meaning of that thing? The physical meaning of that thing is that the magnetic lines of force are always found in the form of closed loop, which means that if we take a point and we calculate the value of divergence at that point, all the lines that are leaving this point will eventually have to come back and enter into it. This means that they always will be equal. The lines leaving and the lines which are entering the point, they will always be equal, and which in turn means that there will be no divergence. So the divergence of B will always be equals to 0, and you need to understand that this is because uh, the magnetic lines of force do not originate or terminate anywhere like electric field lines, because for electric fields we know that the electric field lines basically originate and leave from positive charge, and they enter into negative charge, and they terminate into negative charge. So we always have considered that in electric monopole can exist. We have considered electric monopole so many times, we just did in the last example. We only had a positive charge, but in case of magnetic field, because the magnetic lines of force are always in the form of a loop, we know that there is not a single possibility right now that a magnetic monopole can exist. Whenever we trim down the magnetic material into smaller pieces, we will always have a north pole and a south pole, uh, and you will see that the lines of force will basically come out of that north pole and enter back into the magnet from through the south pole, and then it will come out, and then it will re-enter, and they will always be in the form of a closed loop. So that is why the divergence of magnetic field will always be 0, because divergence is a point phenomena. And basically, while calculating the value of divergence, what we are essentially doing is that we are comparing the number of lines that are leaving a certain point and the number of lines which are entering that certain point. And if it is in the form of a closed loop, every line that exits a point has to enter back into that in order to make it a closed loop. So these were the two basic postulates that were related to magnetostatics, and we have studied these postulates. While dealing with electrostatics, we came to know that d, the electric flux, was equals to epsilon E, and for that equation we uh, adopted an assumption that the value of E will be taken as a scalar quantity, and it will always be a constant value, because we have an assumption that our material will always be a isotropic material, homogeneous material, and the value of E will not change. The same thing that we have in magnetostatics, the counterpart of this thing is B is equals to mu H. He says that as the case with mu, the permeability for this counterpart of permittivity that we had in electric field, we have permeability in magnetic field. He says that we have to follow the same assumption that we did for permittivity, that the value of permeability will also not change with location or with direction like we did in electric field. But there is a difference that for electric field the value of permittivity was always taken to be constant, because we said that the usual materials that we deal with are isotropic and homogeneous. But in case of magnetic materials, there is a certain kind of magnetic material that does not follow this thing, that does not follow this condition, and that material are said to be ferromagnetic material. For ferromagnetic material, the values of B and H, they are not linked linearly with each other. As soon as basically the value of H is the value of magnetic field intensity, and the value of B is the value of flux density that is in any material due to the presence of that intensity. So what happens is that whenever you start increasing the value of H from 0, the value of flux density increases, but there comes a point at which the material is now saturated. So at that point, when you increase the value of magnetic field intensity, the value of flux density does not increases that much. So we will say that that material is now in saturation region. At that point, the value of B and the value of H, they are not linearly linked, because the value of increment the increment in the value of magnetic field intensity is too high, but uh, the increment in the value of B is too low, according to that thing. What is the science behind that, we will study when we'll study the ferromagnetic material in a little bit more detail. But uh, right now, what the goal of me explaining this thing to you is that you should know that how these two things can be compared, like how the electric flux density can be compared to magnetic flux density. The thing is that the permeability will assumed to be constant for most of the materials, but whenever we are talking about ferromagnetic materials, and we will be talking about ferromagnetic materials fairly uh, much more than the other materials, because the ferromagnetic materials are certain kind of materials that we need in different kinds of machines. So in that materials, the value of B is not linearly linked with the value of H, and the reason is that the material goes into saturation, and at that point the linear relationship basically it deviates. So this was the difference between these two things. Now, what is the objective of this chapter? The objective of this chapter will be to develop the understanding of relationships between steady state currents, the steady currents J, and the value of B, like what we have studied in FSC or a metric, when we were talking about the value of magnetic field intensity B due to a current carrying conductor. That is the most simplified version of that thing. So we will need to develop the understanding of the relationship between steady state current that was passing through that conductor, and the value of B, which was developed around it due to the movement of those charges. And apart from that, we will be introducing some related quantities. I told you that that it will be easy for us to study magnetostatics as compared to electrostatic, because in each term that we will study in magnetostatic has a counterpart in electrostatic. Like we have electrostatic potential energy, in the magnetostatics we will have magnetic potential energy. In electrostatics we had electric scalar potential, as comparison to that, as a counterpart to that, we will have magnetic vector potential here. So we will be introducing these kind of quantities, like magnetic vector potential, magnetic energy density, omega m, the inductance. In the electrostatic part of this course, we studied the value of capacitance. Now we will be talking about something which is called inductance, that usually stores energy in it in the form of magnetic energy. So this is basically the objective of this chapter. This is it for today. The next time we will be moving towards magnetic forces and torques. This is it for today. If you want to ask anything, you are welcome to ask your queries in interactive session. Thank you so much.